As part of NASA's Earth-observing fleet, Landsat has been monitoring the planet's health for over 40 years. With stunning images in multiple wavelengths, Landsat provides valuable data to farmers, scientists, and city planners, as well as the public. And behind these images lies QUIP, the Quantum Well Infrared Photodetector, which is processed here in the Detector Development Lab at NASA Goddard. Similar to the sensor in your digital camera or your cell phone, the QUIP detector is designed to be more sensitive and to detect specific wavelengths. Let me show you how these high-end detectors are created. The spectrum of light contains many wavelengths, of which the colors of visible light are a small portion. We have built and packaged detectors to cover wavelengths from microwave to X-ray. The basic goal of a detector is to absorb the energy from a region of these wavelengths of light and turn it into an electrical signal. The first step for us is to take the wavelength, resolution, and the sensitivity requirements of the mission and turn that into a detector design using CAD software. The layout is sliced into individual layers or masks that will be combined during fabrication to create the final detector device. Welcome to the Detector Development Lab. This is a unique Class 100 cleanroom where we have the agility and the technology to develop first-of-a-kind detectors, as well as the experience and the process control to turn those into flight-qualified products. All of the specialized equipment in this lab is used for one of three general purposes: lithography, etching, and deposition. Together, these three processes make up our basic toolset. The first basic process is called lithography. Don't adjust your picture. The yellow lights provide protection for photoresist, a photosensitive polymer that is used to define the detector geometries to as small as 1 micron. The first step in lithography is to apply photoresist to the substrate. This is done by spinning on a liquid suspension of the polymer in the spin coater. The coated wafer is taken to the photomask aligner, where the chrome-on quartz mask that was created by the design and layout is placed in extremely close proximity to the substrate and aligned to existing patterns within a micron of accuracy. A UV light source exposes the photoresist through the mask, transferring the pattern into the photoresist. Finally, the substrate is developed, rinsing away the exposed areas of the photoresist. The next step is to use this protective mask and etch to remove material from the exposed areas of the substrate. We have a wide variety of methods for removing materials, including wet chemical etches, reactive plasmas, and ion sputtering. In one of the most fascinating examples, the deep reactive ion etcher uses short etching and passivation cycles in a high-power ICP chamber to etch silicon hundreds of microns deep with 100:1 aspect ratios. After etching, the photoresist mask is stripped off in a solvent and the substrate is ready for deposition of the next layer of material. Deposition is the third basic process in our toolset, and it covers a wide range of specific processes and materials. During deposition, a thin film of material is added back to the surface of the detector substrate. Materials run the gamut from insulating dielectrics to metal nitrides to pure metals and even superconductors. Here in the atomic layer deposition system, single atomic layers of materials can be built up one by one for precise control of thickness and uniformity. Once the deposition is complete, the substrate goes back to lithography to pattern the new layer of material. In building up the designed detector, we start with a substrate such as silicon or gallium arsenide wafers. Next, numerous iterations of these three basic process steps are applied to the substrate in order to build up the materials and geometry needed to detect the energy of interest, such as IR, define the pixels, and allow electrical readout, while meeting all the scientific requirements for the mission. Here is a gallium arsenide wafer with 16 QUIP arrays that has completed fabrication. The substrate is taken to our packaging lab, where it's diced into individual dies. The die are screened, then meticulously cleaned and indium bump bonded directly to a specialized readout integrated circuit, which converts the raw electrons generated in each detector pixel to a signal that can be interfaced to the instrument's computers. Finally, the detector and ROIC are bonded to the necessary fixtures and PC boards, and the detector subsystem is ready for integration with the rest of the scientific instrument. The Quick Detector on Landsat 8 is just one example of many missions supported by the DDL. We have built and packaged detectors to cover wavelengths from X-ray to microwave in support of missions such as Astro-H, SWIFT, HAWK, Suzaku, and JWST.
Each detector was specifically designed to meet the science and mission requirements, developed, fabricated, packaged, tested, and delivered for integration. These unique capabilities at Goddard have helped NASA to stay on the cutting edge of instrument development and scientific discovery.